Good morning, good afternoon, good evening, class. This is Mr. Arosena, and on today's lesson, we're going to be talking about applications of uniform circular motion. When last we left off, we had discussed the basics of circular motion, so we introduced some of the formulas. So, for example, centripetal speed is calculated as 2 pi r over t, where t is time for one resolution, or revolution, time for one revolution. Right. And then from there we got centripetal acceleration as v squared over r. I'm not sure, I don't remember if I showed the proof for that. If not, there's a link in the description below to a Khan Academy proof, which I think should be understandable. And then from there, we expanded it to talk about centripetal force as mass times centripetal acceleration. And this means then that if I substitute this for centripetal acceleration, I can get centripetal force as mv squared over r. Or if I take this and substitute it into here, I get m 4 pi squared r over squared, where again t is time for one revolution, but I should make note that r is radius of circular path. Okay, radius of circular path. Okay, so that's kind of where we left off as far as circular motion went. So today we're just going to go over a couple of applications of it. All right, so first, when regarding circular motion, there's always going to be a force that causes the circular motion or the centripetal acceleration. And depending on the context of the situation, the force that's going to cause the centripetal acceleration or the circular motion is always going to be different. So presented here are four situations of something going in a circular motion. And I want to take a moment to think about what would cause the centripetal force in each of these situations. And then by extension, that centripetal force would cause a centripetal acceleration. So I'd ask you to pause the video here for a moment, look at the four situations, and then think what causes each of these situations. Then once you've paused and thought about it, you can continue watching the video. All right, so the car going around the corner, the force that causes this car to go around the corner would be the force of friction caused by tires. Friction caused by. So if the tires did not cause this friction, then there's no reason for the car to be traveling in a circular motion. If you're swinging a sling above one's head, the centripetal force that keeps the sling moving in that circular motion would be the tension in the sling. Now, a satellite orbiting a planet, this one might be a little, might not have gotten this one, maybe. Depends. This would be gravity. Okay, so a satellite hanging or in orbit around the planet has nothing is physically attaching it to the planet, so the only thing that can possibly cause it to get closer to the planet or move towards the planet would be gravity. Okay, and here the passenger on a roller coaster at the top of a loop. So if the top of the loop is like this, and you are the passenger here, think keeping you going around in a circle at the top of the loop. Well, there's actually two things that could be working against you or causing you to go there. First would be gravity, one, and the seat, force of the seat. So both of those forces are keeping you going in a circular motion. Okay. So as you can see, circular motion, it can be caused by a number of different forces, all depending on what the context is. Force centripetal depends on the problem or on the situation. And it's really become quite apparent when we start talking about electromagnetism. There's a lot of things in electromagnetism that rely on using centripetal forces, but then depending on the situation, what that centripetal force is will change. Okay. All right. So now let's go through a couple of examples of how we can apply this concept of what causes centripetal motion and how we can analyze it. All right, so this example here is about an amusement park, which I haven't actually seen in quite a while. Possibly because it's too dangerous, I don't know. We'll see. So anyways, so this particular ride has the rider stand against a wall while it spins. Partway through the ride, the floor is removed, but because the ride is spinning fast enough, so because the ride is spinning and rotating fast enough, the riders do not fall. So the key here is how fast, what's the minimum speed we need to spin in order to prevent the passengers from falling. Okay. Now let's assume then that we have a radius of 6 meters and the coefficient of friction of the wall is 0.4. All right, so have a pen and paper out. This would be a good time to take it out and follow along with the examples so we know what we're doing. All right, so here's the problem again, but I've got more room to work with. All right, so first thing I'm gonna do is I'm gonna draw what it looks like for the person pressed up against the wall. So there's my wall. It's the wall. And I'm gonna illustrate the person here. Here's the person. So there, okay. There's the person pressed up against the wall. Now, if I analyze the forces here on this person, I'm going to have a force of gravity pulling me down. There's my force of gravity. Okay. And force of gravity, if there's nothing else acting on this person, then the person is going to slide down the wall. But we don't want that. We want to prevent the person from sliding down the wall. So the only thing that can really prevent this person from falling down is if I have a force going up this way. Now, somebody wonders, like, well, how's that possible? What could possibly cause an upward force in this situation? Well, there is one, and in this case, it will be friction. If you remember my talk, I don't remember if I mentioned it in this class or maybe in last year's class about how to get out of a well if you're stuck in it. Well, one of the easiest ways to do that is to quite simply press your body against the well wall, and that'll increase this amount of friction. So what is this, I guess, this force of friction? What's causing this force of friction? Well, the force of friction is going to be caused by a force pressing you into the wall this way. Okay. So there's going to be a force pressing into the wall this way. Now, what is that force? Well, we'll talk about that in a moment. Now, if this force exists, Newton's third law says that there must be a force going in this direction. Okay. All right. And then we'll label this also an unknown force. So to recap, in case you guys got lost in this explanation, on my person that's up against the wall, we'll have a force of gravity pulling them down. We want to stop that force of gravity, so we're going to try and create friction forces that equal the force of gravity. Okay, because if the friction forces equal the force of gravity, then the person should not accelerate, and if the person is already stationary, then they're going to stay still. Now, in order for the friction to be created, friction, if you remember, needs to be is calculated as mu times a normal force. Okay. In this case, the normal force we'll say will be this one here. That'll be the normal force. So this normal force here needs to get to a point where if I multiply it by the coefficient of friction, it equals the force of gravity. Now this normal force, because of Newton's third law, there has to be another force acting in this direction to equal that normal force. So this force here has to equal my normal force. But what is this force? Well, let's look at my diagram. In my diagram, I am spinning in a circle. So this force here is towards the center of the circle. towards the center of the circle. Well, it turns out that we have a name for that. This is centripetal force. We'll call that centripetal force. Now, after we now analyze this again, so we have got gravity pulling down. To counteract the gravity, we're going to create friction. To create friction, we need normal force. And in this case, the normal force is going to be equivalent to the centripetal force that's pulling us towards the center of the circle. Now let's set up some equations. We know that from previous lessons, centripetal force is equal to mass times centripetal acceleration. But we can also say centripetal force is equal to v squared over radius, or it can be mass times 4 pi squared r over t squared, or t. All right, we don't know my centripetal acceleration, so I probably can't use this formula. And I don't know enough information about its motion, so I can't use this one because I don't know enough about time. And the question is not even asking me for time anyways, it's asking me for how fast must the rider spin. So I'm going to use this formula to help me solve it. So my centripetal force has to be mass times v squared over r. So that's my centripetal force. Okay. Now the centripetal force must equal, the centripetal force is equal to the normal force. But the key here is that this portion here must be true. So the coefficient of friction times normal force must equal the force of gravity of the rider, otherwise the rider is going to fall. So let's continue setting this up. So I know that my force of friction, which is equal to mu times Fn, but then we know that Fn, the normal force, has to equal the centripetal force based on what I mentioned earlier. So I can so I can continue substituting things in. So mu times Fc, but an Fc is really just mass times velocity squared over radius. And this all has to equal the force of gravity, which we know is just mass times g. Okay. It's probably not how your math teachers would like you to write this out, but kind of makes, I don't know, it might make more sense progressing linear this way. So the force of friction is equal to this. We know that normal force is equal to that. We know that that's equal to this expression here, which has to equal the force of gravity, and we know what this. Ultimately, what this means is that this equation, mu times centripetal force over radius, must equal mass times gravity. Okay. And the great thing about this is that, as you notice, this is really important, especially for ride designers, is that the mass of the rider doesn't actually matter. So it doesn't matter how big or how small your rider is. If you design the ride properly and have it spinning at the proper speed, the mass of the rider shouldn't matter. All right, so let's solve for speed now, because that's what we're ultimately asked to find. We're asked to find how fast it goes. So after some algebraic manipulation, we get the following. Times r divided by mu. Okay. And then this ends up becoming v square root of g times the radius divided by mu. G is just going to be assumed near the surface of the planet. We have a radius of 6 meters, and our coefficient of friction is 0.4. Right, so after some pull up a calculator. You guys can probably do this faster on your calculator. So let's hope this does it as I expected. There it is, okay. Square root, whoops. So 9.8 times 6 divided by 0.4 equals square root it. There we go. So the ride needs to spin at about 12.12 meters per second. Rounding this up to proper significant figures, probably 12 meters per second. Although honestly, we probably want to spin faster than that because 12 meters per second is actually smaller than this number. So we want to spin faster in case the coefficient of friction on the rider is smaller than the 0.4 we estimated. So it could be like maybe the person's wearing a really slippery jacket or something like that. Who knows? So anyways, yes, we'd probably want to spin a little faster. So realistically, for margin of error, probably you want to spin 13 to 14 meters per second. Okay, there we go. Now, if you ever get on this ride, know that as long as the riders design the ride properly, you should be perfectly fine and you should not fall off, unless you're wearing a frictionless outfit of some variety. All right. Okay, on to the next example. So in this example, we're going to talk about bank corners for cars. This will usually be, you'll notice this on highway exit ramps usually. Sometimes if you follow stock car racing, you'll see this on their tracks as well, where the really large corners are usually banked in some way. The reason for the banking is because if they're banked properly, the car doesn't have to worry too much about the actual friction as long as they're exiting at the proper speed. Okay, very important for highway exit speeds, and especially in places where there could be icy or wet conditions that reduce the amount of friction on the road. All right, so here, let's suppose then that we want to design a corner with a safe exit speed of 13.4 meters per second. That's around, I think, 50 or 60 kilometers per hour. And we want to design this so that the radius of curvature is 50 meters. Okay, and then we'll decide, okay, what angle should the corner be banked at? All right. So let's scale things down a bit, give myself a bit more room. All right, this will require clever force diagrams. So let me simplify this diagram here a bit. There we go. My car now simplified to a box. All right, so let's analyze the forces on this car. We have immediately one force. We know force of gravity. But force of gravity is usually broken down into this sliding force here, and then this compressing force down like this. Gravity, F pressing, and then F sliding. I'd normally add a friction force here, but we want to make it so that there is no friction, so we won't worry about friction forces. No friction. If it was not a frictionless surface, like if we actually want to take into account friction, then we'd have to put friction there. But for the purposes of this problem, that's going to be 0. Right, and then in addition to the compressing force, we're going to have a normal force going this direction, like so. All right, F, and then this is going to be my angle theta. All right, now, if this was just an inclined plane and the car wasn't moving in a circle, this force diagram is perfectly fine. But because the car is going around in a circle, we actually have, so I'll draw it like this. This car is traveling like that. So going around in a circle means that there actually is some kind of force pushing this way. Okay. Now what is that force? Well, look at my diagram here. Notice how I drew my normal force a little bigger than the compressing force. There actually was a reason for that. And that's because the normal force is actually somewhat bigger than the compressing force due to the fact that the normal force has to provide some kind of centripetal force this way. Okay, so the centripetal force goes that way. In addition to this, the centripetal force, or the normal force, does also have its own y component, like so. That y component doesn't actually matter at this point, but just so you guys know, it does have this y component here. Now, there's a couple things we need to do in addition to this. We need to figure out what are the angles in this new right triangle I've drawn where the normal force forms the hypotenuse of this right triangle. Using parallel lines, we can show that this angle here has to be theta. Okay? And since the normal force is perpendicular to the sliding force, that means that this angle here, so this angle here has to be 90 minus theta. But really the easier way to think about it is that the angle up here has to also be theta. Okay, and this will become very important when making for the problem. This will make it easier for working with some of the trig when we work through these. Alright, now we've got that taken care of. Now I gotta figure out a couple of things. We want to know what the angle is. So in order to know the angle, we need to know what FC happens to be. Okay, so C is. Okay, well, FC has to be mv squared over r. That's the information we're given. Okay. Now, FC also happens to be same as the opposite component of this triangle, and if you remember from SOHCAHTOA, the opposite component is sine theta equals opposite over hypotenuse. So if I rearrange that, then the opposite side has to equal hypotenuse sine theta. So if FC is the opposite side, the hypotenuse is Fn, so this has to be Fn sine theta. Now look at my diagram here. Look at the diagram. What is Fn then? We know that Fn has to be bigger than F compressing. So in this situation, Fn is actually not equal to the compressing force. It's actually going to be a bit bigger. Okay, but I can still look at my diagram here and look at, if I mentioned earlier, that this y component has to be equivalent to the force of gravity. And that's because if this y component here were not the same as the force of gravity, then the car would be pushed into the ground, or the car would start floating above the ground, which we don't want. Okay. So looking at this diagram here, see Fg is the adjacent side to the Fn, so I can use cosine to figure out another expression for Fn, because cosine is A over hypotenuse, so hypotenuse will be A over cosine theta. In this case, A is the adjacent side is Fg, so I can write the following. Fn is Fg over cosine theta, and then times sine theta, and that will equal my centripetal force squared over r. Now at this point, hopefully some of you remember some of your trig identities from pre-calculus 12, because what can I do with sine over cosine? Can I simplify that? Hopefully yes. Sine over cos ends up becoming tan theta. Alright, I'm going to replace Fg with its formula, mass times gravity. Squared over r equals mass times gravity times tan theta. And much like the other problem, notice that the mass will cancel out, because if the mass of the car mattered, then designing these roads would be quite a pain. You have to think of a single car that could possibly be traveling along. Thankfully, the math shows us that the car doesn't actually matter. The only thing that matters is how fast the car is going and what the radius of the curve is, which thankfully we know. We want to make sure the car has a safe exit speed of 13.4 meters per second. So 13.4 meters per second. We want to build the exit ramp to be 50 meters. And G, I'll just divide the G to the other side. So 9.8 meters per second squared, and that'll all equal tan theta. All right, let's pull out the calculator. All right, so let's do this. So 13.4 squared, 4 divided by 50 divided by 9.8. Okay, so tan theta will be 0.366. 366 equals theta. Inverse tan that. Tangent, so the angle about 20 degrees. So approximate angle about 20. Yeah. So if you build the road with a bank of 20.1 degrees, cars should be able to travel around it at 13.4 meters per second without falling off. Falling off could mean whether it is sliding up this way or sliding down that way. Okay. Now suppose that we didn't have friction. Suppose we did have friction. This would change the equation slightly, slightly, because you'd have to take into account, well, the friction forces, this friction force would cause a horizontal force this way and a vertical force this way. So then the normal force would then have to take into account that this upward portion of the normal force has to counteract force of gravity and has to counteract the upward force due to force of friction. Similarly, the centripetal force then has to also counteract the force of the horizontal part of the force of friction. So the equations become a little bit more complicated. Just more things to keep track of. Okay. All right, so there's that example. All right, let's do another one. Example 3. Example 4. This is the loop one. So this one is, if you do the math for this one, you can actually figure out minimum drop heights for various things like roller coasters, even the Hot Wheels cars. If we were in class, this would probably be the next lab we do, is to calculate the minimum drop height for loops and then see how close we are to correct. Anyways, so let's suppose we want to design a roller coaster with a radius of r. Okay, so notice there's not going to be any numbers in this, so we're just going to be entirely algebraically manipulating. We want to know what is the minimum height the roller coaster needs before the loop in order to safely make it through. And then we're going to assume that no loss of energy. Due to friction. Now, this will give you a big clue as to how we go about solving this problem. Okay, so to solve this problem, let's analyze what's happening at the top of the loop. So let's just grab this over. I can up a bit. So at the top of the loop, we'll take darker. So there we go. So at the top of the loop, are experiencing a centripetal motion this way. So that centripetal motion or centripetal force, properly designed, should have at the very least equal to the force of gravity. Ideally, you kind of want it to be a little bigger than the force of gravity, because then the opposite force that's going this way is bigger than gravity and keeps you in your seat. But for the most thrilling ride, we want to make it at least equal to force of gravity. If the centripetal force is not equal to the force of gravity, then gravity ends up pulling you down faster than you can go around the corner and you end up falling out of the loop. All right, so that's the minimum, at least. So at least force centripetal must equal force of gravity. All right, so this means then that centripetal force mv squared over r has to equal at least mg at the top. Okay. Now, one of the things that a lot of students make the mistake of thinking is that, okay, my drop height only needs to be the height of the roller coaster, but that's not entirely true, because if your drop height is the height of the roller coaster and you're analyzing this using energy, then if this is my drop height, remember that we had our potential energy, total energy, kinetic energy. So potential energy here equal to mass times gravity times h. And if your drop height happens to be the same as here, well, your drop height, the start of the drop generally has a kinetic energy of 0. So if I have a kinetic energy of 0 at the top of the loop, what does that mean for this equation here? Well, if you remember, kinetic energy is mass 1/2 mv squared. So if I have 0 kinetic energy, I have 0 speed, which means if that's true, I have 0 centripetal force, which means that gravity is pulling me straight down at this point. Okay, so we cannot have the drop height to be the same as the minimum as the loop height, because then that means that our kinetic energy at the top of the loop is 0, and then the gravity will pull us to our doom. So the height has to be high enough that when I get to this point here, so this point here, I will have some potential energy, but I will also have some kinetic energy. Okay, and this kinetic energy is not 0. Okay. That's very important. That's very important. Okay. Now look at my equation that I've written down here. Looking at this equation here, you should see that again, the masses will drop out. So at the top of the loop, what this allows me to calculate is that at the top, my speed, so my v squared over r, must equal g at the very least. Okay, and then rearranging this to solve for v, or I guess v squared. See why I'm leaving it as v squared in a moment. V squared must equal gravity times radius. Okay, keep this in mind. You could actually square root this, but for the purpose of this equation, leaving it as v squared is actually going to be a little more useful. At least easier to work with. Okay, if you want to find the actual speed, yes, you'd have to put in the number. So if your loop is 100 meters in radius, then put 100 meters here and calculate. But for now, let's leave it like this. All right. All right. Now, at the top, we know that this is my potential energy and kinetic energy are added together. So potential energy we can calculate as mass times gravity times height. But instead of height, I'm going to use, because this height here, so the height of the loop is basically twice its radius, so we'll just go 2r. So the height will be 2 times radius. Now the kinetic energy will be 1/2 mv squared, whoops, not equals, plus m 1/2 mv squared, like so. Okay. All right, so this is at the top. This is all at the top. At the top, this is the energy. I can then take this and replace v squared with that, because I know v squared is equal to gravity times radius, so I'm going to do the following. M times g times 2r plus 1/2 mg. So there's the total energy at the top. This is equal to total energy. Total energy. Okay. At top. So we have a potential energy represented by this equation. There's my potential energy. My kinetic energy has now been somewhat simplified to this. That's my kinetic energy. And adding them together gives me total energy at the top. Okay. Now, we're interested in, well, what is the drop height? So if I were to draw this, there's my loop. What is this height? That. Okay. Well, if I'm doing this like any other drop problem, then I can say the following. Okay, well, at the top of the loop, I know that, or at the top of, not the loop, top of the drop, my kinetic energy will be 0, and my potential energy will be mass times gravity times height. And therefore, much like the energy problems we were dealing with previously, the total energy at the drop height has to equal just potential energy plus kinetic energy. But we know kinetic energy is 0, so that'll be 0. So mgh. So we'll set this, the total energy at top of loop must equal mass times gravity times height. Alright, so let's rewrite this. So this, the left side of this equation represents the total energy at the top of the loop. Right side represents the total energy at the top of this drop here, just before the loop. Now, one really cool thing you should notice is what happens to all the masses. Well, the masses all drop out, which is good, because then it doesn't matter who's riding the roller coaster. It did matter, then things would get ugly. The gravity also drops out. So this actually works on no matter where you are on the planet, or heck, even the universe. Now we just simplify things. All right, so 2r plus 1/2 r, that'll be 2.5 times the radius. Okay. Well, so as long as you construct the loop and the drop height just before the loop is 2.5 times the radius of the loop, then your car or roller coaster or whatever should have sufficient energy to clear. Ideally, you'd want it to be higher, so I should change this to greater than or equal to height. Not greater than, just make it greater. So greater than. That's to leave room for error on. So a good designer will leave room for error. So the height above the height, this height here, or the first drop before the loop, needs to be at least 2.5 times the radius, preferably more. Now, if you have a Hot Wheels track at home, I highly encourage you to do that. Is to the Hot Wheels loop is like that. Measure the radius. Easiest way to do that is basically measure the height and divide by 2. And then see. Well, if I know the radius, then if I'm dropping my car from a height of at least 2.5 times the radius, then the car should have sufficient energy to go through. Provided, of course, that your car isn't scraping along the Hot Wheels track or causing undue amounts of friction. Okay. Now, interestingly enough, what if you had 2 loops? What if you had 2 loops? What would this minimum height be? That'd be something you could try. Previous physics class of mine did it, and the result was actually quite intuitive. So give it a try. Give it a try. All right, one final example. Okay, and this one is quite interesting because it gives us a way of possibly creating artificial gravity. It's something that's always glossed over in science fiction about gravity and where gravity comes from. But here's one possible way to do it. And you'll actually see this in some old science fiction movies or TV shows. The one that comes most prominent to mind is like, what show? Babylon 5. Yeah, Babylon 5 illustrates this quite well. A few others that illustrate this. Anyways, so we want to construct a space station in Earth's, that can simulate Earth's gravity. Given what we learned, what is the best way to construct a space station? Well, we've done a lot of making things equal to other things, so we'll do the same thing here. We want to rotate this space station, basically. Because if I rotate the space station, so if the space station rotates, then we can give the illusion that centripetal force creates a force of gravity. So let me draw a circle. So let's say I have a space station. and I have a person on this space station. It doesn't matter where this person is on the space station, as long as it's rotating. So in space, we have basically no gravity. Well, very little gravity. And if you want to simulate Earth gravity, well, if I rotate my spaceship, then this centripetal force will give the illusion that I have some kind of gravity acting on me. Okay, now it might look kind of strange. It's like, well, but why? Because the force of gravity, or the centripetal force, is pulling me towards the center. Why would that be? Well, Newton's third law tells us that there has to be an opposite force going in the other direction. This is going to be, we'll call it, I don't know, we'll just call it approximately force of gravity. It's not really the force of gravity, but it gives you the feeling of the force of gravity. So if I'm rotating this space station fast enough, or if I make the space station big enough and rotate it, because remember, the centripetal force is v²/r. So I can have two options. I can either rotate the space station really fast, or I can make the space station really big and rotate it slower. Regardless, the result will still be the same. If I can get some combination of speed and radius and rotate the spaceship, or space station, then I should be able to create a centripetal force that mimics the force of gravity. Okay, and this is really important because our bodies are designed to operate within the gravitational effects we feel on the planet's surface. If we don't, a lot of our body systems will weaken, like our muscles, our bones, and things like that, which is a very real problem for astronauts. Like long-term space missions, and when astronauts come back to Earth, their muscles are quite a bit weaker. So we've had to come up with clever ways to keep muscle mass, keep muscle strength up in space. Because again, our muscles are designed to operate under a certain amount of gravity, and if it's not there, then they weaken over. There you go. Anyway, so yeah, so there's some applications of circular motion. The highway one is probably the most easily observable one if you if you ever drive on the highway or drive anywhere there's exit ramps. This example will probably be, you guys might live to see something built like this. Maybe. I probably won't. Anyways, there we go. So some applications of circular motion. If you haven't done your project yet, then you can feel free to add this as one of the, you can feel free to use this as one of the situations you might want to look for, and especially in science fiction. Okay, your assignment for today then will be, oh, wait. You can do that on your own. I think one of your assignment questions has that. Now let's just do this. So how fast would I have to spin to simulate Earth's gravity if the radius was 5 kilometers? I already have this set up here. And this has to equal the force of gravity. Okay, I'm just clean it up over here. Squared over r must equal the force of gravity. Thankfully, masses cancel out, which is really important. Okay. We want to calculate the speed, so I'll just rearrange it. So speed, the rotation will be 9.8 meters per second squared, and we have a radius of 5 kilometers. 5 kilometers, so 5,000 meters. Remember to convert to meters when necessary. All right. This, so 9.8 times 5,000, and then we'll square root that. So I have to rotate my space station at 221.3 meters per second, or with proper significant figures, about 220 meters per second, give or take. Okay, that's if you want to experience actual full-on Earth-like gravity. Give an idea of how fast that is. That's, let's see, 100 kilometers per hour is about 26 meters per second. So that's almost 1,000 kilometers per hour. That's really fast. We probably wouldn't rotate that fast, or we'd make the space station a lot bigger. Anyways, there we go. All right. So your assignment then for today will be as follows. I'll have a link for it in the description below. If you have any questions, you guys know how to contact me.